first thing that we want to discuss is how we can do learning rate scheduling. So what do I mean by learning rate scheduling? So this is one step of gradient descent, right? So you get your weights, you just subtract the gradient, and then you use one particular learning rate, right? So we typically, I mean, up to this point, I always told you just a fixed learning rate, right? So that eta was somehow fixed, but you don't really need to keep it fixed. And you can just schedule it through time. This means that in every single iteration, you look at your gradient, you look at the result that you're seeing, and based on that, you decide what you're going to do with that learning rate, okay? One classical approach is that you start with a large learning rate because you can think that, okay, well, I'm starting somewhere randomly. The function is still steep enough, far away from the optimum point. So I'm going to just take long steps, right? But then you gradually start to reduce it. This is like the most naive, classic, say, way of doing this scheduling. And you can have different forms of scheduling, right? So you can do it linearly, like linearly you drop it by this step. You can do it polynomially, you can do it exponentially, and so on, right? This is going to help in some simple cases, but when the problem gets more complicated, again, this one is not very sophisticated. But just to give you a kind of idea of what we mean by learning rate scheduling. One other classical approach is that you just like wait for the saturation of the test risk. So when you are training in every single epoch, you are going to check the results, right? And you are just plotting the test results, right? And then at some point you see that the test loss is somehow getting saturated, right? So this means that with the learning rate that you are working right now, right, there is no hope that you get better, right? If you see that, then you start to drop it. And how you drop it? You drop it by a factor smaller than 1. Like you say, okay, let's a couple of iterations go on. And after a couple of iterations, I see that the loss is not dropping anymore. So somehow I can think that if I am around an optimum point, like the minimum point, I'm just jumping around it, right? I'm not getting close to that anymore, right? So I started to get closer and closer. Maybe I was just moving around it. But I got into a point where I am somehow locked within a vicinity of that, right? I'm not getting any more further there, right? And what is the idea? Okay, maybe I can drop the learning rate. Now that I drop the learning rate, I stop oscillating, and maybe I get towards that, right? So you do this, so you get into this sort of saturation. Then you would say, okay, at this point, maybe we can update the learning rate, right? So you reduce it, check if you can go further down, right? And if you again saw a saturation, maybe you can again try updating it, right? It doesn't mean that you always see this very nice graph, but this is again one solution, right? Okay, so in practice, this learning rate scheduling is a very good thing if you are really doing a hardcore implementation. This is going to help you a lot. But typically, we're going to use available packages in libraries. So for example, PyTorch, it has its own library, which you can use to do learning rate scheduling. One thing that you should keep in mind is that by doing learning rate scheduling, you are eventually not changing the convergence speed. So it doesn't mean that your speed is now going to be linear, right? So you're still sublinear. So if you remember, we talked about that you are just talking about that constant time, which is getting scaled, right? And then you are trying to reduce that constant time, right? But you are still getting scaled by 1 over epsilon, right? Which is still a lot, right? But if the constant time, like the fixed time that you need is small, then that 1,000 times fixed time is going to be smaller, right? So this is the only thing that you are doing when you are doing learning rate scheduling, okay? Any question on this? Everybody's clear? So nothing specific. The only idea is that you come up with a solution, with an idea, that you somehow manage to change the learning rate in every couple of iterations, okay? So this is what we call it learning rate scheduling. And the second way that we can somehow handle the challenge is the idea of momentum. So what is the momentum? The momentum is basically working based on the fact that we know the gradients we are computing are some sort of random gradients, right? So they are not exact true gradient, they are estimators of that gradient. And now the point is that when I am estimating with a small mini batch, this means that in every estimate, in every particular iteration that I compute my average over a mini batch, this guy could be very variant, right? It could be very noisy, it has high variance, and it could just jump around the true direction very harshly, right? Now the question is that is there a way that we somehow filter out this variation in time? And the idea is basically to do a momentum. What is momentum? Momentum is basically the moving average of the gradient. So anyone knows what is moving average? Anyone has any idea about moving average? I'm going to explain it right now, but no one. OK, so just pay attention. I'm going to explain it in details. So what the idea says that, well, when we are using SGD, we are basically doing an estimate of the true gradient, right? We want the true gradient, but we cannot compute it, so we just find an estimator. That is the one you compute it on a mini batch, right? Now, the idea is that then when you want to update, you're going to get your weight. You just subtract it from the minus, or subtract it from the estimated gradient, right? Now, momentum says that instead of gradient, just use the momentum, just the moving average of the gradient. Now, what is the moving average? This guy is the moving average of a one process in time, okay? Now, what are we doing here? Let me just write it down on the board. So what I am doing here, instead of working with G, so G is a gradient sequence, right? G in the first iteration, say initial G, basically we did not have any initial G. So G in the first iteration, G1, then you change the iteration, you get G2, G3, and you keep on going, right? So in time t, you have GT. So basically you're observing this sequence, G1, G2, and so on, GT, right? Correct? So everybody here is a kind of noisy estimator, right? So there was one smooth sequence, so they say G tilde 1, G tilde 2, and so on till G tilde T. This guy was the true gradient, right? The gradient when you had infinite data, and you could use all of it to compute your gradient, right? Then what you're getting here is basically this guy, plus some noise, right? So you're getting here plus some epsilon 1, plus some epsilon 2, plus some epsilon t. And you keep on going, right? And this epsilon could be very high variance, right? So this is what you're seeing. And what you want to do, you want to somehow get rid of the challenge here with epsilon, right? You want to reduce the impact of epsilon. Now, the fact is that this sequence that you see has also independent noise processes, right? And if you average it over time, this noise variance is going to drop, because we know that if we just average a random process, we're going to reduce its variance, right? Everybody sees that? OK. Now, let's look at this one, see what it's doing. So say I want to compute M1, and I start with M0. So the very first, the initial value of the momentum is 0, right? Let me tell me what is M1. What is it? So beta is a value between 0 and 1. So what is it? 1 minus beta times G1, right? So the first guy is 0, so it's going to be 0 plus 1 minus beta G1, right? Correct? OK. Now, what about M2? What is it? Beta M1 plus 1 minus beta G2, right? Now, what is M1? M1 is 1 minus beta G1, right? So it's going to be 1 minus beta g1 times beta plus 1 minus beta g2, right? Correct? Now, look at this guy. If I add things up, it's going to be beta minus beta squared plus 1 minus beta. So beta is going to cancel out. It's going to be 1 minus beta squared, right? Right? The coefficients, you see that, right? So this guy, this number, is something between 0 and 1, right? So this is smaller than 1, more than 0. This guy is again some number smaller than 1, more than 0, right? More than 0, more than 0, right? You see that, right? So now, if I just call this guy to be a coefficient gamma 1 and call this guy to be a coefficient gamma 2, then I could say my M2 is gamma 1 times G1 plus gamma 2 times G2, right? Now, what about M3, if I want to compute M3? Can you tell me? What is it? It's going to be beta M2 plus 1 minus beta G3, right? Everybody's clear? Exactly. So what's going to happen if I take this one and put it there? It's going to be beta gamma 1 G1 plus gamma 2 G2 times plus 1 minus beta G3, right? Everybody's clear? Now, just expand this guy again. This is going to be beta gamma 1 G1 plus beta gamma 2 G2 plus 1 minus beta G3. Again, call this guy to be, I don't know, alpha 3. Call this guy to be alpha 2. And call this guy to be alpha 1. Okay, what's going to happen? It's going to be alpha 1 G1 plus alpha 2 G2 plus alpha 3 G3, right? And if I keep on going, I can always write down any m. So if I am talking about any mt, I can always write it down. So if I replace this guy with mt, right? So let's this guy be 3. Now if I replace here mt, this is going to be this summation, keeping going till alpha t gt, right? Everybody agrees, right? You see that? Questions? Cool. Now, one thing. Alpha 1, for example, here. What is this number? Can it be more than 1? No, because I told you gamma 1 is smaller than 1, right? Then beta is also smaller than 1. This guy is smaller than 1. This guy is also smaller than 1. This guy is also smaller than 1. You can go ahead at home, and for any arbitrary t here, you just compute the summation of all of these weights, and you see that this summation is also smaller than 1. It's actually always ending up one specific form, 1 minus beta to power t. Okay? And then when you write that down, what do you conclude? What is it doing? It is basically averaging the g values that you had, right? So you got g1, g2 till gt, and you are just multiplying with the coefficients, which are between 0 and 1, and their summation is something fixed, which is smaller than 1 again, right? Correct? So it's again a sort of averaging on g. So if we think of g in this form, what we are doing, we are basically averaging out these values of epsilon. And because of that, the momentum could somehow show a smoother behavior as compared to the gradient itself, because gradients are noisy samples, but momentums are somehow average over time, which is much smoother, and this somehow can help you jumping in the direction, right? So, any questions? Yeah, you got a question? Yeah, sorry. The sum of coefficients are not 1, but they are something fixed. It's going to be 1 minus beta to power t, I guess. And then if you divide everything by 1 over beta to power t, then everything normalizes back to that one. But the key point is that these weights are not going to get more than 1, right? So they are always adding up to something bounded, constant. Okay? Yeah, you can.
So essentially you're doing a weighted average with higher weights for the more recent values?
Exactly. Exactly. That's correct. So you are giving higher weights to the recent values because obviously, I mean, it depends. It depends. If you want to talk about this, you basically should look at the momentum expression. So it depends on the beta. I mean, in practice, we choose beta to be close to 1, 0.9. And this means that you are giving more weights to your current momentum. But your current momentum is average of whatever you have seen up to this point, right? And this is a kind of valid choice because you would say that, OK, this average is less variant as compared to what I see new, right? But if you look at this in this form, then you would say that the impact of very early gradients are going to vanish eventually, right? So you mostly concentrate on your recent gradients. But at the end, you're somehow, if you think in terms of the momentum, in every time you still give higher weight to your recent momentum to your momentum as compared to the new gradient, right? If you choose beta close to 1. If beta is 0.9, for example, which is in practice the case. And this is because your new gradient is going to jump up and down a lot, right? Yeah, but the momentum is not going to change too much, right? So now you can try at home, generate one random sequence, and then compute the momentum. And you see that as the time passes, the momentum starts to just change very smoothly, whereas the gradient, I mean, every sample could just harshly change, right? Okay? Questions? So you got the idea of momentum, because this is important. I mean, people use it all the time in different applications. It's important that you understand what the moving average does, right? Now, any idea that any sort of problem this moving average could make? Not that you should see it immediately, but if you see it. If I am doing moving average, so say these true gradients that we were talking about are there. I mean, they are definitely there, right? And I'm averaging over time. Now, this gradient in time 1, in iteration 1, is it the same gradient as the guy in iteration 2? No, we changed the weights, right? And the gradients are going to change, right? So when we are averaging them over time, these guys are going to get mixed, right? So meaning that the gradient that you get at this time is not exactly the gradient of this iteration, is this one, if you forget about the noise. Is the gradient of this iteration averaged somehow with the gradient of the previous iterations, which are not valid anymore, right? This is why using momentum going to make a bit of bias in your learning, because it's going to somehow shift the direction of the gradient towards a direction which is not exactly the case, right? So if you want to think about it, is that if I am in one particular iteration, the right direction for the gradient is like this, right? If I do stochastic gradient descent without momentum, then I could just have a variation around it, right? This means that I could just go this direction, right? I could also go up to this direction. Now, if I want to think randomly, then sometimes I go here, sometimes I go here, right? And I jump around this direction. But in average, I'm exactly in the direction that the true gradient is, right? But when you use momentum, you're just shifting a bit your direction, right? And this is coming from the bias you collected over time, right? So the true direction is this direction. You should go this way to minimize, right? But you're shifting a bit, right? But the benefit that you get is that you are not jumping anymore too much, right? So you're jumping around it slightly, right? So you walk around it slightly. But the problem is that you have a bit of bias, right? You get it, right? OK. So this is a kind of issue that you can see. But in practice, if you choose beta properly, and if you think that, I mean, you know, the function has a bunch of good properties, then this bias could be negligible. It's not going to impact hugely on your training process. So So moving average is going to have less fluctuations because you are averaging over time. And this is going to give you less variance in your gradient. But this is coming at the cost of a bit of bias. But that's OK. So this is then the algorithm. I mean, whatever you had in SGD, you can do the same thing. Now, every single iteration, so here, before this line, you just did your back propagation over your mini batch, right? And once you finish with that, you got your gradient, right? And then you just average your gradient with your momentum that you had in the previous time. This is going to be your new momentum, and then you update, OK? So this is only this particular line getting added, just moving average. Everything is as before. So what you did as before is the same, just before you update, you just compute the moving average, right? Questions? Yeah.
What happens if you, when you're close to the minimum and you just reduce the beta, then it will just.
Well, yeah, you can do that. You can do that, but in practice, we are not going to do that because if you think like you're very close to the minimizer, then the gradients that you are collecting are all roughly close to 0, right? And you're only seeing those noises, right? And by averaging through time, they are going to vanish, right? So this momentum is also going to get close to 0, right? Just look at this expression on the board, right? So if, say, you started very close to the minimum, roughly this guy is 0, 0, 0. All of them are 0, right? So you are averaging zeros plus some random noises, right? And those noises are going to average out, right? So yeah, you can do that, but really in practice you don't need to. Yeah. And this is going to give you much more efficient convergence as compared to naive gradient descent, right? Yeah. Increasing value of beta actually reduces the variance. It's going to increase the bias. Because when you increase beta, you are giving more weight to your momentum, right? And your momentum has less variance, right? But it has a bias, right? It's going to have more bias, right? So now, question on that. Everybody's clear on this guy? So as I said, in practice, typically you choose beta value to be quite large, close to 1. So 0.9 is a typical choice. And the reason is because you don't want huge variance, right? You want to rely on less variant samples of gradient, okay? So the basic SGD that you have in PyTorch, it actually has momentum. And then you just choose the momentum coefficient, that is beta. You just put it 0.9, and then you're going to just do the SGD using momentum. OK, so now there are other ways to compute momentum. There are basically numerical tricks. One of them, which is very famous, is the Nesterov one. And the Nesterov idea is basically to do the same thing. OK, so it's still momentum in the sense that you have a gradient, and then you're going to average it with your previous momentum. So this is the time average, the moving average of the gradients, and then you update. So everything as before. The only difference here is that when you want to just compute your gradient, you don't compute your gradient exactly at the same as before. Like you just change the weight a bit. So what is the idea? Before I show the expression, let me just explain it intuitively here. So say that I am at this point, OK? This is the point that I am at time t, at wt minus 1, OK? And now if I want to get to wt, OK, this is the direction I go, and I get to wt, right? What is this direction proportional to? If you look at this expression, look at it here, right? So if I have, or maybe I have it t and t plus 1, it's OK. So let's call it t plus 1, OK? What is this guy? Wt plus 1. This is Wt minus learning rate, mt, right? Set learning rate 1 to just get rid of it. what is the direction that you are going to? The momentum, right? So this guy is momentum at time t, right? That's correct, right? So if I am at one weight, when I update using momentum, I just move proportional to minus, right? But I just drop the minus as well. So minus momentum, I'm going to get to the new point, right? Everybody's clear? Yes, it's opposite. I mean, I just want to say this is proportional to momentum. I mean, everything is negative. OK, keep the negative here. Everybody's clear? Right? OK. Now, what is momentum at time t? If you look at that guy. That is beta momentum at time t minus 1, right? Plus 1 minus beta, some gradient, right? Some gradient at time t, right? Correct? I have not computed the gradient yet, right? But what I do know is that if I have this particular point in between, which is w hat t, okay? This is one point in between. And this direction is minus beta mt minus 1, okay? Then this guy is actually minus 1 minus beta gt. Do you agree with me? So what is going to happen? If I replace mt as this form inside the expression of the gradient descent update, so my wt plus 1, this guy is going to be wt minus, I said set the learning rate 1, right? So this is mt only, right? Correct? And this is going to be wt minus, OK, mt, you just replace it from here. Beta mt minus 1 minus 1 minus beta gt, right? Everybody's clear? Right. So this guy is what I called it w hat t. So this is somehow I get from wt to w hat t first, right? And then I update by my gradient, right? Everybody agrees? Questions? Oh, sorry. Is it better now? Okay. So everybody agrees on that? So what we are doing when we are updating with momentum, we are starting from some weight. We just move somehow with the coefficient of the previous momentum. We get into a new point, and then we update from that new point into our next point, right? Next weight. Somehow we are doing that. Of course, we are not doing that exactly. We are just moving directly to that direction based on the momentum we computed. But this is somehow happening that we are doing this two-step move, right? Now, the question is that this gradient that you want to compute, this guy, why should it be the gradient at this point, at this weight? Why should it be at this weight, right? Why shouldn't this be the gradient at this point, right? Because when I am in iteration t, I already know mt minus 1, right? I haven't updated my momentum yet. That's true. But I have the momentum from previous time, right? So I get from here to this point, and then I compute the gradient and update this one, right? Is there any harm in doing that? Well, given the fact that we are averaging gradients over time, no, there is no problem, right? Because this gradient, of course, is not the gradient at this point, but anyway, I don't really know that if I need the gradient at this point, right? Actually, if I think about this point, then I could say that I am just updating with the basic SGD, right? And then this is the right gradient that I should look for instead of the gradient at point WT. Everybody sees that? So this is the only difference of the Nesterov. What Nesterov does is that before it goes for computing the gradient, it already updates the weights using this expression. So there is no backpropagation, anything involved here, right? Because before you start doing your backpropagation, you already know the momentum of the previous time, right? So when you want to do the backpropagation, instead of just doing the backpropagation on the weights that you have, you just do the backpropagation on this adjusted weight, right? And the reason that you adjust like that is because you want to somehow approximate the middle point, right? And then you would say, well, the gradient of that point would be probably more useful as compared to the gradient of the start point, right? Questions? So this is what we call it Nesterov. Usually when you use momentum in PyTorch, you have this option Nesterov true or false. And that is basically by doing this, this is going to give you more robust sort of convergence. Okay? So, now, if you look at the expressions usually you see in the implementations, people just make it complicated because they take this W hat and they directly replace it here. And then it makes it a bit complicated, but you don't need to. I mean, that's exactly this one. Whatever you see is exactly this one. Yes?
You believe that starting from that one will be a better choice?
A better choice for computing your gradient, right? Because at the end of the day, you have a mini batch. You want to do backpropagation over that to just compute a gradient, right? The only question is that should you keep the weights as they are, or should you update it with some this line, which is basically harmless, right? So you don't need to do any extra computation. You have your previous momentum, right? You just need to update your weights. So it's somehow saying that, OK, I already know that at the end of the day, I'm going to get to this point W hat, and from there, I'm going to end up in WT plus 1. So maybe I go there and get to compute the gradient more close to the point that I want, right? Yes? For the basic momentum, yeah, for the basic momentum is the same thing without this update of W hat, right? Okay. It's exactly the same as the previous one. We just update the weights before we compute the.
I know, but just like the value for WT plus 1 is different, right?
It's different, definitely. Right, exactly. This is different, and this is the main reason that you do that. It's going to be more reliable. Statistically, it's more reliable because you are somehow computing the gradient at the right point for SGD update, right? But this is just a bit of more statistical description. No, it's not more closer point necessarily, no.
In terms of direction, it might be more accurate.
Yes, because this guy is going to be unbiased estimator of the gradient of this point, right? This GT that you compute at this point, then you are going to update exactly with that one, right? And you're updating with unbiased estimator, right? Because of that, this is going to help more. But I mean, the main idea is that you are somehow approximating the next point before you start computing the gradient, right? Questions? Yes, but one of them does not need backpropagation, right? Yeah. And so this is nothing, right? Yes.
So do we say in some extent the objective is always to update the model as much as possible? Because going from full batch to mini batch and then going from the momentum to the Nesterov is always updating faster if we can.
Yes, if you do it with smaller paces, smaller steps, that definitely going to help. If you can find any way that without super extra computation you can update better, yeah, definitely. I mean, intuitively this is going to help. Yeah. So, everybody's clear about Nesterov? Questions? No question? Great. So if you go in PyTorch, you can just use SGD as I told you, and here you have both Nesterov and momentum. Usually the choice for momentum is 0.9. This is a good choice. And one thing obvious is that if you set beta equal by 0 in all that formulations, then you're going to get back to the vanilla SGD, right? Because if, for example, here beta is 0, every single time I'm just taking beta is 0, weight is not getting updated, and then the gradient is exactly the gradient at that point. So this is the vanilla basic SGD, right? And then when you increase beta, you are giving more, some weight to momentum. And the more weights you get, the less variance you're going to see, but you're going to have a bit of bias, right? OK. So that's regarding the momentum approach. Another thing, another idea that people came up in modifying the optimizers was the idea of dimension or dimension-dependent update of the learning rate. So if you remember, we had this assignment, in assignment 1, there was one question where you had 2 parameters, 2 weights, right? And then you discussed this, that if you have 2 separate learning rates for each of the dimensions, then eventually you can do better as compared to having just one single learning rate, right? Because that one could eventually help you just move towards the optimal point in one step, one shot, right? Whereas here, with one single learning rate, you cannot do it, right? So this was a kind of idea for a very long time. So people said, if we are just updating a multidimensional function, if we can have for every single dimension a separate learning rate, right, like I am not moving in this gradient direction with only scaling the direction, right? Every dimension, I just scale it separately, right? And then if I can do that, then eventually this is going to help us much more in terms of convergence, right? And then one of the ideas that could somehow implement it was Rprop. So the issue in practice is that your function is huge in terms of dimension, right? So if you want to do it manually, it means that if you want to do it by designing a process which looks at every single dimension and does the update separately, then it's going to be a huge loop, right? So you need to go over every single dimension. This is impossible. You want to come up with a sort of automatic approach, right? And Rprop was one of the pioneering, or say, dominated, sophisticated ways of doing this. So what is the idea of Rprop? Let me first do it for one dimension. Now that you get it for one dimension, for multi-dimension, you basically do it in parallel for all the dimensions, OK? So what is the idea? So in the one dimension, you have only single weight, right? This is the only weight that you have. This is not a vector anymore. This is a scalar, right? You have W. You want to update it. How do you update? You're going to subtract from learning rate times the gradient, right? Now, one thing that you can do is that when you are working with one dimension, you can only focus on this sign of the gradient, right? Correct? I can only focus on the sign of the gradient. This is going to be the same thing. If it's positive, it's going to remain positive. If it's negative, it's going to remain negative, right? And now, that amplitude of the gradient, I can somehow put it inside the learning rate, right? This is not going to harm anything, correct? So instead of having eta being fixed multiplied by gt, I could say I have sine of gt only, and then I multiply it with some learning rate which is changing over time, right? You agree, right? This is the same thing, correct? Now, the question is that, is there a way that I come up with computing this one directly, this learning rate, directly from GT itself? So this is what the algorithm does. This is the Rprop scheduler. So it's basically a sort of learning rate scheduling, right? But this is relying on the fact that you only look at the sign of the gradient, and then you use the gradient itself, the behavior of the gradient, to specify the learning rate. Okay? Now, how does this scheduler work? The scheduler works like this. So you have some positive, more than one mu plus. So mu plus is more than 1. So if I multiply it with something, it's going to increase the amplitude of that thing, right? Now, you start from one basic learning rate, and you keep on going. Now, one thing that you see is that sign of your gradient in this iteration is exactly same as the sign of gradient in the previous iteration. What do you conclude out of seeing that? You're still going towards the minimum, right? So this was your function. The gradient first said we're doing one-dimensional here, right? So it was telling us go forward, right? Again, we went to the next iteration. It still tells us go forward, right? So it means that the minimum is forward, right? I should keep going. So since the sign of the gradient is not changing, maybe we can increase our step size, right? So what you do, you get this mu plus, which is more than 1, and you multiply it with the previous learning rate that you had, right? So you started with a small step like this, and then you see, oh, the gradient is still forward, so I'm going to take a longer step, a longer step, a longer step, and I keep doing it as long as gradient each time tells me the same direction, right? Everybody's clear? So you do it. Typically what you do, you just limit it with one maximum value, right? So you don't want your step size to get to infinity. So you would say, OK, I would take at most a step size 1. So I start from 10 to the power minus 3. I increase it every step. But if I reached out that one, I'm going to stop, OK? This is when the sign of gradient is not changing. But what's going to happen if you just move? I mean, here the gradient tells you go forward, and then you take your step. Now the gradient tells you go backward. What do you conclude? You have passed the minimum, right? So you need to just go back. Now, if you want to go back, do you go back like with the same step, longest step, or you're going to take a smaller step, right? Because it would say it was somewhere in between, right? So this is what you do. You just choose one mu minus, which is smaller than 1. If you see that the sign of gradient is changing, then you just scale your learning rate with that, a smaller than 1 coefficient, right? So it means that you're reducing the size of your gradient. So what is happening here is basically, as you see the sign is not changing, you keep on going faster and faster and faster. But once you see the sign is changing, then you start to just reduce your pace, right? So you're going to make it slower, right? Everybody's clear? So in one-dimensional case, this somehow makes sense, and of course you're going to have again a minimum eta, a minimum learning rate under which you're not going to reduce, right? So yeah, so this is somehow a diagram explaining the same idea. So you start here, you see that, well, you computed the gradient here, you get this point, right? When you get to this point, you see the same sign of the gradient. So for the next step, what you're going to do, you're going to take longer step, right? For the next iteration, you're going to take longer step. So here it was positive, you increase. Here it was still positive, you increase. You keep on increasing, but at some point you start to see, oh, the gradient tells me go back, right? So what you're going to do, you're going back, but now you are going to take a smaller step, right? And you keep doing this, right? Now, what is happening here is that you're somehow scheduling your learning rate, right? This whole process is like you decide for your learning rate, right? But for scheduling, you are not doing anything but looking at the gradient, right? Which is a feasible thing, right? So you can write a function. It takes the gradient, basically this function. It takes the gradient. It computes the learning rate every single iteration, right? And you can do it automatically. So this is what we call it Rprop. And if you want to just do it in multidimensional case, you basically do the same thing. So you have your giant gradient, right? You do the same thing in parallel on every single entry, right? So this means that you're going to get your eta for every single entry is scheduled by the gradient component of that entry, right? So in the algorithm I showed you, you just give the entry of that gradient, right? That particular entry of the gradient. And after that, you're just going to update all of them in parallel using Rprop, right? Yep. Yep.
Does mu minus need to be greater than 0?
Definitely. Yeah, it's greater than 0. Yeah, both of them are positive. Oh, sorry. So yeah, but they cannot be negative, right? Yeah, I didn't mention anywhere positive, but I mean, obviously, learning rate is always positive. If you make it negative, then you are not doing gradient descent. You are doing gradient ascent, right? Yeah. It could improve. It could improve. It's not making it linear, definitely, but it can improve. Right. Right. This can improve. Yes. Sorry?
Does the absolute value?
No, the absolute value of the gradient, you don't do anything with it anymore. You just use the sign, right?
When you compute the linear rate,
When you compute, sorry?
when you
I mean, you just use the sign of the gradient, definitely, right? And you somehow leave the amplitude to be taken care of by the scheduler. Yeah. I mean, this is not the best you can do. I just wanted to give you the idea. Then we're going to get a better variant of that, which is practical. Yeah.
Could you do it instead of the magnitude of the gradient, and as the gradient gets smaller, it gets smaller?
Well, if you do that, then you're going to get back to the basic gradient descent, right?
Basic gradient descent doesn't update the learning rate as a
No.
So if you update the learning rate as a function of the magnitude of gradient.
Oh, this is what we're going to do next. Yeah. This is a basic idea. This is not going to work very promising in practical scenarios. Then we need to actually include that one as well. Yeah, we're going to talk about that. Yeah. Questions? No question? Okay, so these are classical choices for mu plus and mu minus. So 1.2 is a classical choice for increasing. Half is a classical choice for reducing. And usually eta max and eta mean are less important because, I mean, it's a very impossible case that in practice you always keep the same sign, right? You're going to jump at some point, and that is not going, I mean, the explosion is not really going to happen. But you can keep some large number for them as well. One other thing is that if you just would put 1 over mu plus equal to mu minus, then this means that if you took the same step increase, then you're going to do the same step decrease for the next time, which is not necessarily a good idea, right? So if you don't do that, it's better. So you see, for example, here, I don't have it. 1.2, 1 over 1.2 is not half, and this is OK, right? But if you do that, still, you're not going to just see a huge problem. So, yeah, again, you can access it simply in PyTorch, and then you do know what are those parameters if you want to use it. One last thing about the Rprop is that if you use Rprop, this idea that we said, this is going to eventually work only when you do full batch training. So if you do full batch training, if your gradient is super reliable, the one you are computing is very low variance, then this is going to work fine. But when you have a gradient which is high variance, it means like you're doing mini batch, then this is not going to work very fine. And what is the reason? Well, you can do a bit of math to understand it, but that is not really necessary for this course. So this is why I'm doing it again with a dummy example. So let's do this dummy example. Let's assume that I have one-dimensional case. So I just have one weight, OK? And now I have a quiet, small data set. And I just break that data set into 4 mini batches, OK? So I have 4 different mini batches. And now what I do, if I compute the gradient at the first mini batch, this is 0.1. Second mini batch is 0.2. Third mini batch is 0.1, 0.1. And the last mini batch is minus half. OK? Now, can you tell me roughly, not exactly, roughly, if I would have had computed the full batch gradient, what would it be? Any idea? And I don't know, you cannot say the exact one, but roughly. What is it? You could say, yeah, almost 0. But what you could say, you could average these 4, right? Because one of the gradients is on the first mini batch, right? The second gradient is on the second mini batch, third mini batch, last mini batch, right? And the average of all of these mini batches is the full batch gradients, right? So you could say that roughly average of these guys is the full batch gradient. So as you said, this is roughly 0. But you could say like minus 0.2 divided by 4, it's going to be minus 0.05, right? But this is not exact because you compute this gradient here in one iteration. This is another iteration, and so on. This is not the exact gradient you see if you do full batch. But you could roughly say if the gradients in every iteration is small, then this is roughly the case, right? So you agree with me that the gradient is roughly close to 0, right? Yeah. And then the sign of the gradient could be positive or negative, because at the end of the day, I don't get the exact gradient. I'm computing an estimator of it, right? And if it has a tiny bit of variance, it could jump plus or minus, right? Now, what you're going to see if you do Rprop, in Rprop, you're going to look at the first mini-batch. This is positive, right? Say that you started with a positive gradient. So it's still positive. You're going to increase your step size, right? You go for the next one, you again increase your step size, right? You go for the next one, you again increase your step size. Now you get here, you see, the sign change. Now you decrease, right? But the point is that you really did not need to increase so much, right? Because these 0.1, 0.1, these were probably just because of noise, right? Because of the randomness of your gradient computation. And with the same chance, this 0.1 could have been minus 0.1, right? You agree? You see that? So this is the issue with mini-batch training with Rprop, because Rprop is relying on the sign, right? And if you're working somewhere like here, close to 0, then this sign could be very variant, right? Because your computation is noisy, right? And, well, relying on that could simply lead you to nowhere, right? Take you somewhere totally lost. So if instead of 0.1, the gradient was like 10, 10, 10, and then here minus 8, then you could somehow rely on that. Because you could say, OK, 10 is a very large one. I mean, even if this is a noisy, if it has a high variance, it still cannot be the case that I am just, it is changing the sign, right? But in this case, you cannot rely on it. So what you can say is that, like using the Rprop, you're going to take the first 3 steps, which are taking you more and more far away from the point. And then finally, the last one, you want to take a smaller step backward. Whereas if you think in terms of full batch, the whole gradient is roughly 0. You don't really need to update too much, right? Everybody agrees? OK. So this is the problem that you see with the Rprop used for full batch training, mini batch training. And to come up with some solution for that, we go for what we call it RMS prop. And